Hello and welcome back. If you follow the channel, you know that we just got a magnificent HP 115BR divider and clock from a generous patron. This instrument was famously used in the 1964 flying clock experiment, riding atop HP's prototype portable atomic clock to synchronize all the world's atomic clocks for the first time in history. In part 1, we explain how this unit worked without using any ICs, by the combined magic of regenerative dividers, resolvers, synchronous motors, and optomechanical tick generation. We also found that our unit is extra special, having two factory modifications. The first one to increase its precision by a factor of 10, like the one used in the 1964 flying clock, and the second one for adding a 60 Hz reference output. But sadly the dividers did not work, so our generous patron worked out a third modification, disconnecting the dividers and using modern electronics to generate an internal 1 kHz instead. That made the clock motor run again, but it sort of defeats the main purpose of the instrument, which is meant to generate a super accurate time and precise 1 second ticks from a high stability crystal or atomic oscillator. So in this episode we will try to return our 115BR to its original condition and hopefully end up with an atomic steampunk superclock. So now that we understand the noodly schematic diagram, the removal of the added modern 1 kHz oscillator should be rather simple. We'll remove the oscillator and its yellow wire connected to pin S, and repair the cut original HP green wire from S to T. That should reconnect the regenerative dividers to the clock motor, restoring the instrument to its factory modified condition. Okay, first order of the day, remove the customer made modification. It shouldn't be that difficult at all, now that we understand it. Ooh. Except I have to remove the pen to do it cleanly. And I don't have the... Not my favorite way to do it. I much prefer to extract the pin. I don't have the extractor. Go. Not my favorite way of doing this. Okay, and that should have reconnected the two dividers. That should have reconnected the output to the motor. So we will hear something. The next step is to try it with a 100 kHz input, which I'll derive from my HP 3310 function generator. HP conveniently provided a BNC input for the test. And I should have 100K on the scope, it's down there. Alright, so here we have 107. Okay, let me get 100 exactly. This is my reverse engineered board. The new first regenerative divider, which Alan tells me he has repaired. So it didn't work and he changed something. I know what it is. That's this transistor. This doesn't appear original. Alright, before we dive into the debugging, here is a quick recap from part 1. The clock input signal is a 100 kHz frequency from a high stability crystal or atomic oscillator, impersonated by my beloved HP 3310A signal generator in this test setup. The 100 kHz is sent to a first regenerative divider, which divides it by a factor of 10. Starting from the output of the divider, the 10 kHz goes into two tripplers, bumping it to 90 kHz. A mixer produces the 10 kHz from the 100 kHz and the 90 kHz. And around it goes again. To break the chicken and egg problem of getting the 10 kHz output in the first place, a 90 kHz start oscillator is used to temporarily jumpstart the whole thing. Yep, you have to crank up your divider. This is how the genius HP engineers implemented this in practice, using only 4 early germanium transistors. Q201 is a limiting amplifier tuned to 100 kHz. The mixer is transistor Q202. Mixers are so easy, just put anything nonlinear like a diode in the circuit and mixing products will result. So easy it even happens when you don't want it. In our case, we want it, and the nonlinear element is the emitter-based diode junction of transistor Q202. Using the transistor's emitter-based diode as the mixer is a dirty trick that results in a mixer with gain. The 10 kHz mixer output signal comes out at the collector, which has two tuned LC circuits as loads to reject all other mixing products. The first tripler is transistor Q203, driven hard into cutoff to generate distortion with a strong third harmonic component at 30 kHz. Said harmonic is then filtered by the resonant LC circuit in the collector. The second tripler, transistor Q204, is identical, save for the value of the resonant LC circuit, now at 90 kHz. This tripler also incorporates a dirty trick. It doubles as the 90 kHz start oscillator. It is simply transformed into an oscillator by allowing positive feedback through the temporary starter switch S201. So if this thing works, we should be able to pick up all sorts of frequencies. 100 kHz at the collector of Q201, 10 kHz at the collector of Q202, 30 kHz at the collector of Q203, and 90 kHz at the collector of Q204. This should be highly entertaining when viewed on the scope. So it's over here somewhere. The first divider is in this area here. 4 transistors and T202. Oh, T201 is over here. T202 is over, 203 is over there. That should be my signal out. So that should be 30 kHz. Let's see if we get divider action. Just turn it on. Nothing at all. What is that? Okay, oh no, we get something, but we have to start it. I did start it. I think it works. So this is 100 kHz that comes in. Then I have 30 kHz at the tripler and 90 kHz at the second tripler. But at the output I don't have 10 MHz. What the heck? This is 100 kHz. Let me check my wiring here. Something's not quite right. Okay, this is so completely three-dimensional. C222 is actually all the way over here, but it has been deconnected with the modification, so I think now the output is over here. That's what I think it is. Let me try. Let's see. Yes. Yes. I do this. Now it's 10 kHz out. So if I put them in order, 100 kHz, 90 kilohertz, 30 kilohertz, and 10 kilohertz. Which is kind of sort of neat, right? Why use ICs to do division where you can do it with RF only? Okay, so the first divider seems to work. I can realign it and tweak it, but for now it's fine. Woohoo! Our first miracle divider works. That's mostly thanks to Alan, the kind patron who donated the instrument, as he told us that he had managed to repair it by replacing a dead transistor. But then we come to the HP modifications. In the standard 10 microsecond resolution instrument, the signal goes on to the second divider, then to the phase shifter. But in our factory modified instrument, I now believe that the phase shifter has been rewired and resides between the first and the second divider. Let's check if my assumption is correct. Plus, I am really curious to see if the strict phase shifter, relying on an electromechanical resolver principle, truly results in a continuously and endlessly adjustable phase shift. For the next experiment, I'm going to check if my understanding of the modification, the HP one, is correct. So I should have 10 kilohertz come out. I have it now, and then it should come through that thingy, and I should be able to change its phase. And I've hooked myself up at the receiving end after the phase shifter. I should have 10 kilohertz here and then another 10 kilohertz here, but with an adjustable phase. At first I get nothing because I have to start it, right? Boink. And I have two 10 kilohertz, so that's the one we just got before, and that's the new one. Can I adjust it? Ooh, you bet. Ooh. Look at that, continuously adjustable. And this is 5 microsecond per division. Yeah, and it's totally continuously adjustable. That's the beauty of resolvers. They have no limit, right? Awesome, okay. Excellent, excellent. We confirmed that the modification is working as we thought and that we have a good phase shifted input to our second divider. So the next logical step is to check, say, its second divider, which is an almost identical circuit to the first one, except that it now takes 10 kilohertz in and gets 1 kilohertz out after having generated 3 and 9 kilohertz through the triplers. So same thing, just 10 times slower. Piece of cake, right? So now, okay, let me wire myself up since I know I have the input signal. So we should get 1, 3, and 9 kilohertz. All right. Okay, next experiment. I should have my 10 kilohertz, the phase shifted 10 kilohertz, then the 9 kilohertz, and then the 3 kilohertz. And then if that's all appear, then I will assume that I should get 1 kilohertz out of the mixer. So of course at the beginning we don't get anything because we need to start it. So oh, so I'm hearing the 1 kilohertz done at the starter. My probe is not attached well. But I'm not getting the 3 kilohertz. Okay, so the second divider is not working, but part of it wants to work because I suppose if I could start it right there. There you go, I could start it, but it doesn't maintain itself. We're making progress. There is something not working, but very little. There's just something in that circuit. After that, everything started working. So let me think for a minute. That's the circuit. That's the 10 kilohertz, and I'm measuring it right here. So it made it through this transistor. It's fine. I could get 9 kilohertz when I did that switch, which means get this stage to self-oscillate. That's the second tripler. And you can see this is my phase shifted 10 kilohertz. This is my 9 kilohertz where I was holding the switch, and it's 8.981, so that's perfect. And I heard the motor, so I got the 1 kilohertz out of here. I looked at the output of this and there was no 3 kilohertz, so it's this stage that would not be working. Let me see if I can just test transistor Q303. And you know what I could do actually? I could instrument it, we should see the 1 kilohertz when I'm starting the oscillator. And I should see right away if I'm getting 3 out of it. Okay, I shuffle things around. This should be my 10 kilohertz in, my 9 kilohertz. Do okay, the 3 kilohertz and the 1 kilohertz. And my expectation is that I'm going to get 1 kilohertz but not 3. So this will test both sides of the transistor, we suspect. Nothing when I don't start it. Start the first divider, have 10 kilohertz. So I do have did it say 1 kilohertz? Low signal, we don't know. I have something very low there. How come? Okay, yeah, I do have 1 kilohertz, I believe, but not that much amplitude, and absolutely 3 kilohertz. We do have a problem right here. I have 1 kilohertz, not that much, only hardly 1 volt, so that might not be enough. But it's not amplifying a bit. So I check my suspect transistor on the ohm meter. It looks good. Good germanium voltage dropout, 0.2 volts across the junction. So I'll take it out, but I don't think it's that. Oh, okay. You unscrew it, and there it is. Okay, so my little transistor is right here at the end of the leads, and as I expected, it is a good transistor. The first step is a little bit abrupt. Looking at it again, this is a bad transistor masquerading as a good transistor. It's a transistor, but only above a certain base current. Weird. I have a spare of these, so let me check an equivalent one and see if it looks the same. Okay, here's another one, and this one also looks more normal. So I am wondering if the one we had still a transistor effect, but something has gone weird with it. So let's replace it. Okay, so I've remounted my transistor in its weird little mounting thingy. It gives you weird vibes, like this is an instrument that was done very soon after the tube instruments, and the mechanical guys haven't quite adapted yet to the transistor. They need to put it in something that makes it look bigger so they can deal with it. This is really tube construction with transistors are forced their way in. So let's see if it's any better. I'm not feeling confident here. I haven't found a nice big bat fault. That, yeah, I still don't have 1 kilohertz, not unsurprisingly. Aha, it looks like we are experiencing the curse of the loopy regenerative circuit. Circuits functioning in a loop are notoriously hard to debug. This is curse number 1. And you are double cursed if the loop sort of half works, like it is here. It is much easier if there is a big bad fault in the loop with a good signal that abruptly turns into a bad one at one stage. But in a half-working loop, the fault propagates all around and you don't know if a bad signal is a cause, an effect, or just passed around by an innocent stage. then like here, you can get triple cursed with a component that's half working like our bad transistor. But now it appears that we are quadruple cursed. We have more than one fault in the loop. This is going to be interesting. So there's a bias issue. I'm so close. Why don't I have anything there? Okay, I am starting to suspect that my mixer is not working and my tripler is working. So I compared the first mixer with the second mixer, and basically the triplers are the same circuits. At the input of the divider that works, I get like 3 volts from the mixer. So I decided to do the same experiment where I inject 1 kilohertz from the oscillator directly with the required number of volts, so I should get tens of volts at the output. So what I usually do to break the curse in this situation is to literally break the loop. I disconnect it at some point and inject a known good signal just after the break point. Here I suspect that I have repaired my first tripler, but that the 1 kHz signal coming out of the mixer is too weak. So I'll break the loop right here before the tripler and inject a known good 1 kHz at the right amplitude into it. If I'm correct, it should fix things downstream, then I'll know that it's the upstream stuff that's bad. In our case, that would be the mixer stage. So I have this, it's injected right at the first tripler through a capacitor, and I look at what's before a tripler and what's after a tripler. Turn this on, nothing. Turn on the generator and get it to 3 volts. And I have plenty of tripled output, and I can hear it coming down the pipe. So I have 20 volt peak to peak of output. It's nice and resonant. That is fine. So let's turn that off. So what doesn't work is the mixer. And the mixer, man, there are that many things in it. There is a transistor. It could be that I don't have enough signal here. I have to check that too. Well, at least let's do that right now. Yeah. So that's my problem. When I try to start it, I have the 9 kHz coming out loud and strong, but I don't have enough 1 kHz coming out of the mixer. The green and the blue should mix to make a strong red, and my red is not strong enough. Okay, mixer not mixing. All right, that's my problem. Alright, it looks like my break the loop strategy bore fruit and that we have identified the faulty stage as the mixer. But there is very little to it. It's a transistor and a tuned circuit. So it has to be either the transistor or the tuned circuit, right? Right? And here go the mixer transistor. Alright. Any bets? Oh, it's a perfectly good transistor. So the mixer is not working, but the transistor is working. Ooh, that's going to make our life difficult. I don't have enough 1 kHz at the output, and I know the transistor is good. So that sent me looking in another direction. Maybe it works, but it's not tuned. It should be very resonant at 1 kHz, and it's not. So what I did is I injected 1 kHz here, and I'm going to test if this is resonant and if this is resonant. It should be resonant at 1 kHz, and I don't even power anything. This is totally powered off. So ignore the blue for a second. There we go. So here is my 1 kHz. Is it resonant? Well, yes and no. The resonance is completely offset. The resonance is at 700 Hertz. and should be at 1 kilohertz. And now we're going to power the thing up. And here we have nothing on the output of the tripler. But there you go. I went far down in resonance. Now I am at 750 Hertz. And I have some tripler output, which amusingly enough is at 3 kilohertz. So the thing is so resonant that it still resonates at 3 kilohertz instead of 2100 or 2700. So my guess is that my let's turn that off. Let's get this point. My tripler is working, my mixer is working, but the circuit is shooting into is at the wrong resonance. Is at resonance at 750 hertz. So I'm going to make another experiment to see if the rest is detuned, because it could be that this output is detuning it. So I'm going to move myself to the output over here, pin 7. I should be with you in a second. Okay, I'm back. So I am now injecting 1 kilohertz here. Check the resonance of the first coil at pin 3 and check the resonance of the output coil at pin 7. That's entrance winding, that's the exit winding. And they don't resonate at the same frequency at all. So if you look at the blue, it is resonating at 1 kilohertz. It's perfect. It's right on the money. But for the primary of the transformer, it's resonating completely off. It's maximum around here, which is 600 or 700 hertz. This is weird. It's so far out of tune. So it's either something I don't understand or it's something to do with the tuning. So let me futz with the tuning. There are values for capacitors with an asterisk. You're supposed to tune them, so I have to find where those are. And I have to remove capacitance. That's so weird. Okay, there's still something not quite fine with my theory, but it's not normal that I don't get the maximum on both of the coils at the same time. Something is cheesy. So the plot thickens. I looked for a tuning capacitor and it's at the back, and it's this fellow right here. Let me center it. So I'm going to remove it and see if that gets me back into range. There we go. Okay. And it does not appear to help the situation that much. So the blue curve is still the output. It's maximized at 1 kilohertz. And the green curve is even worse. It's 650. Now if I put the cap back in place, doesn't make any change at all. So I'm getting more and more perplexed. I need to remove capacitance from the main branch, because even with 0 I'm still too low. So that would be this. And these capacitors are very annoyingly, they are right here. And I have disconnected them to see if unloading them would do a difference. They suggest that in the manual when you tune the circuits, but it doesn't do a difference. So in the end, that still didn't work. I had to disconnect this and remove the entire capacitance of this thing to get it to resonate a little bit more. And I tried to bypass the whole circuit and so run it without capacitor and have a slight capacitive coupling to here. And yes, I could run it. It would sing at 1 kilohertz, but it was looking at all the forms, so I think there is something else going on. So my next bet here is maybe there is a biasing problem, and I'll replace all the 4 microfarads. I happen to have some here from the previous repair, and get those tantalums out of the way. Maybe that will get us back to something that makes more sense here. So there will be those tantalums here I use everywhere for biasing. Slurp. One. Okay, we're hooked up again, all new caps, and we'll see if the proverbial bad cap was it, because if it's not that, we're kind of running out of components to suspect. Alright, so we have to start first, and we did start the first divider, and then okay, that seems to work. I have a fairly dirty... Oh, but that's right at the output of the mixer, so... Well, wouldn't you know it? It works! The dirty blue curve is because I am right at the output of the mixer before the filtering to remove the parasitic mixing products. Seems to work. There you go. I have a working clock. Phew! Gee-wee. Bad caps, and I bet you if I test them, they all test good. It was a leak or something. Actually, I was wrong with the caps. 3 of them were the advertised 4 microfarads, but 1 that just looked just like the others is 400 and something picofarads, so he has lost his mojo. So this is why the rest of the clock works. The other caps are good, but I probably will change them anyhow. But we had a real bad one. I'm going to test it for leakage also. It's hard, but definitely that was a biasing problem. Very tricky. Yep, and it leaks too. So bad cap. That was our problem. Okay, but does it work? So I connected all our outputs, and we'll see if it gives us, as advertised, the frequencies and the phase shifted tick. So I just turned it on, and I have the 100 kilohertz. That's what I'm driving it from the oscillator in the scope right now. So if I get the 10 kilohertz started, there it is, and then we'll get the 1 kilohertz started, there it is, and then I still don't have the 1 second, because the 1 second it needs the it's derived optically, right, with the light and the holes in there. I don't know if you can see the light. It's hard to see over there. Yeah, you can see the light. So now that the clock is started, I should get a pulse now and then. Oh, there it is. There we have it. Okay, there it is. All right. Nice. This was a tough one. We can rejoice for a moment. However, we are not completely done yet. There is still one thing that doesn't work, the second modification for the 60 Hz reference output. In the last episode, we discovered that it was generated by an added board driven by a second photocell. This board doesn't appear to work. There is still one thing that I think doesn't work. That's my 60 Hz thing. And I suppose it's supposed to be a square wave or something really strong, and it's very noisy, and it's at 100 millivolts. And that's the second feature of this clock that's undocumented, but I reverse engineered it. That's what's on this little thing, and it's totally independent from the rest. It's just an amplifier. Actually, I think it should give you a square wave looking at this. So I'm going to look at it and figure it out. Okay, I got the last feature to work. Here's my 60 Hz. And what I discovered is that it was just out of adjustment. There was nothing wrong with it, but just there are 2 adjustments, and these were completely off. What this is in oscillator at 60 Hertz, followed by a buffer amplifier. And what you have to do is tweak it so it hardly oscillates at 60 Hertz, but it's not enough to sustain itself. And when the signal comes in, it brings it into oscillation. Let me demonstrate. If I turn it off, no signal. If I turn it on, you see, it oscillates at 60 Hertz, but it's going to die off. But now, I'm going to start the clock. It's kind of awkward. And with the signal from the photocell, that's going to make it oscillate. So that's how they generate a nice sine wave out of a few transistors. Okay, so I'm all done. I changed a few more of the caps, the 4 microfarad tantalums, just in case, although they were still good. And I removed the modification, so now it's back to what it should be. Put the plate flying on its own wings. And right now I have the 100 kilohertz generated by the scope, but of course now we want to connect it to a high stability frequency source, and that's why we turn to our 106B, waiting for its time down there. That should be it's the highest quartz oscillator, highest quality quartz oscillator HP made at the time, and it's meant to go with this clock. So let's switch restoration and move that one on the bench. Alright, we will next try to reunite the clock with its HP 106B double ovenized crystal oscillator and challenge Eric to synchronize it to within the advertised 1 microsecond of an atomic clock using the magic tick adjustment button. But to top off this episode, there is something I had to try at least once. And now, just for kicks, I had to do it at least once. I hooked up the clock to the cesium reference frequency standard, and finally I have a true atomic clock. And that is actually the config that they used the first time they flew an atomic clock to synchronize the time across the world. And they used this very clock at the top, and they would measure the difference between clocks around the world, cesium clocks around the world in several labs, using that little millisecond dial that we just have here. There's actually a picture of this setup and of it entering the plane before it made its trip in 1960 something, early 60s. The first time clocks were standardized, atomic clocks were standardized around the world, thanks to that instrument. Very historical.